Hello, everybody. Welcome back if you are a frequent webinar participant or just be very welcome to the DuPont Water Solutions Academy. Our primary speaker is Garth Parker Jr., and he'll be hosting you today on a deep dive into the water application value engine, Wave software. Today's format, as you can see, is a little different. I'm here live on video, joined by Garth and two special guests, Kevin Clark and Matt Roth, who will work along with Garth during his demonstrations as your membrane and ion exchange representatives today. So Kevin and Matt, do you want to introduce yourselves and maybe share some of your background in relationship to Wave?
Hi, everybody. This is Matt Roth. I'm joining in from Philadelphia. I support ion exchange resins and water treatment applications, and I'm excited to be here. I have been a part of Garth's Wave team focused on ion exchange for roughly the last 5 years, and I use Wave all the time. I use it almost every day, and being a frequent user of the program, I know there are a lot of features that are less obvious, and I'm excited to share some of that with you today and walk through some examples with Garth.
Hi, Kevin Clark. I'm a manager for membranes for North America for technical services, and I've been working with Garth on Wave since the beginning on the UF SWAT team, and I'm excited to be here to introduce some of the advanced features to you. Laura?
All right, thank you too. Okay, I'm so excited to get going, and we'll finish up with the rest of Garth's introduction in just a minute. We really hope you enjoy this free webinar program and make the most of the engagement tools by downloading your certification of attendance, making questions, and sharing your feedback with us. So we are now offering PDH credits in our certification program, and this was convenient from your feedback, so thanks for the great suggestion, and we hope you enjoy the new feature. So just before, just before I get started, sorry, just let's take a minute for general housekeeping. You can access all engagement resources from the bottom of a screen by simply clicking on the colored icons, and you can resize and move them around as you wish to best fit your screen. So this is a deep dive. You may already have the program, but for those who are interested, you can find a link to download Wave in the resource list. We'd appreciate to hear from you, and the best way to raise your questions or comments is the purple Q&A box on the lower left corner. If your question is longer, or if you'd like to have a more personal response afterwards, you can do that with the blue Contact Us button. Please do submit your questions throughout the webinar. Matt and Kevin will be monitoring the Q&A list as they come in, and if possible, they will introduce questions to Garth as relevant. Though please understand, some may be saved for the final Q&A session. To earn a printable course certificate, you just need to make for the first 30 minutes of this webinar. And know that this presentation is being recorded, so you're going to be available for on-demand view. You can always come back to the content and refer it to your colleagues. Now back to our topic, and I'm happy to finish the introduction of our speaker, the Wave architect. So Garth Parker Jr. is a research scientist in the Technical Service Development Group of DuPont Water Solutions, based in Philadelphia, United States. He has worked for 32 years for Roman Haas, Dow Chemical, and DuPont, primarily in applications development and modeling of water treatment technologies. He has been the technical leader of the Wave development team since the project's inception. Garth has a PhD in chemical physics from the California Institute of Technology. So I hope you enjoy this new format and opportunity to interact with our technical experts live today. Garth, is it time to fire up that Wave engine?
Okay.
Thanks, Laura. Garth, yeah, if you can share your screen. One of the unique features of Wave is the ability to generate multi-process designs combining UF, RO, and ion exchange. So could you go ahead and generate a quick multi-process case, and Matt and I can introduce some advanced design features along the way?
Okay, thank you, Kevin, and welcome everyone to our Wave demonstration. And we'll, as you said, we'll get into some of the features that might not be known to everybody. So we're currently building ourselves a UF, RO, and ion exchange mixed bed design. There's the RO. Now we'll drop in the technology icon for our mixed bed. That goes. So we have chosen the technologies we're going to use. We have set the flow rate we're going to use, 1,000 cubic meters an hour. We've chosen a standard North American river, and now we'll start with our design. The first thing for any process that starts with a membrane is you want to make sure that you have specified what your solids content is along with your water type. These numbers work together to set many of the defaults and operational limits for wave. For a UF system, you would need to specify your turbidity and your TSS. Notice, based on these inputs, Wave has made a recommendation on the correct subtype. Here it's NTU less than 50, TSS less than 30. These are used to set the defaults on the next screen that we will look at. We've now gone to the main UF design screen. The key thing that you need to specify on this screen is what module you want to use. And for this one, we're going to use the SFP 2880XP. Having specified the subtype and the module, almost all of the values, default values have been set. And if you want to just work with a basic design, you're now ready to move on. The next thing one must do is actually pick a configuration of online trains, modules per train, things like that. Wave provides a little table here that would help you understand if you need, in this case, about 30 modules, how you could configure that between trains and modules per train. There are advantages for more trains or less trains, but if you keep the total number of modules about the same, the hydraulics stay fairly comparable. But there would be differences. For example, if you choose more trains, when there are interruptions in flow due to cleaning, you get a smaller change in flow if you have more trains. So we'll choose this one by double-clicking on it. If you want to see a very simple system summary in UF, you have this little table here, and you can see what the recovery will be, then the flux, and an overview of the hydraulics. Okay, we'll take the rest of the defaults for UF, and we'll move on to our RO system. On the RO home screen, the key things you need to specify are the number of stages that you want. In this case, we're going to choose 2. The number of pressure vessels per stage. In this case, I'm going to take 10 and 5. The number of elements within each pressure vessel, I'll stay with the default of 6. And then you need to specify the element you want. At this point, Wave has everything it needs to know and can move on with defaults. Going on to our mixed bed polisher, there are a couple of things that you need to enter to at least get a default configuration. Number of trains. Here I want to have 1 operating and 1 in standby. You need to specify whether you're going to run a design based on a length of a cycle, or for many mixed beds, we will specify the specific velocity or the spatial velocity, 35 BVs an hour, and Wave will use that, the size of the vessel, and then calculate the runtime you could get. We want to use a mixed bed, so we'll specify a mixed bed with internal regeneration. We have to choose a resin. We'll take HPR 1200H, HPR 4200. For regeneration conditions, we'll choose hydrochloric acid and sodium hydroxide. And we'll take the defaults for everything else, and we can now run our design. And we now have our basic, very simple Wave report. You will get a tab here showing the summary report for each of the technologies, which the idea of a summary report is to provide enough information for the designer to know that they have a valid result with no major problems. So usually a summary of the hydraulics, a summary of water quality, and design warnings. And in this case, there are no design warnings.
Garth, if you can move back to the UF design module. You talked a little bit about feed water quality, and feed water quality is closely linked to UF cleaning, things like solids loading and organic loading, but also the feed water temperature, which has an impact on cleaning kinetics. And a typical maintenance wash strategy that we use with our UF is chemically enhanced backwash, where you're dosing chemical in line with the backwash water. But one of the limitations there is that you can't really make large adjustments to chemical concentration. It's difficult to switch out chemicals, and you've got no facility to heat up the clean to increase the chemical clean effectiveness. On the other hand, another cleaning strategy, like a mini CIP, has this sort of flexibility built in. Could you show how you can select between these different maintenance wash protocols within Wave?
Sure, Kevin. Right now, we have the CEB button selected on the side here, and you can see the operating conditions that were the default for the CEB. If you want to run the mini CIP that Kevin just mentioned, you can go up here to the UF special features, and you'll have a drop-down that allows you to specify the cleanings. Usually, it would be the CEB only or the mini CIP only. There's very rarely would you ever do both in one process. So the CEB screen has disappeared. We now have a mini CIP screen, which specifies the various chemicals that would be used. If we just pop back to the design, you can see that we're going to be doing our mini CIP once a week, as opposed to previously we were doing the alkali cleanings daily. So now we can rerun the report, and there'll be some subtle changes in the results because the changing of the cleaning protocol changed how much water was used for the cleaning protocol, and therefore we had more water on average going downstream to the RO and mixed bed system. And this bought us an extra 0.1% in recovery.
Now, in some cases where you're using UF filtrate for the CIP makeup water, there could be some concerns if the feed water is high in hardness or has a lot of sulfate in it, that there could be some interactions with cleaning chemicals leading to precipitation and scaling. Can you show how we can select other makeup water sources for those cleans?
Sure, Kevin. We go back to our UF module, and we look at our cleaning protocols. And if you have a RO system as part of your design, you can click on the water type for our mini CIP, and you could use RO permeate water to make up your solutions. And we'll do the same thing for the CIP, and we're going to use RO permeate. You'll notice changes in tank size. We also now have a blue line coming in showing you that your CIP water is coming from the RO system. And if we run the design, you still see we have the RO water coming in. If we go to the reverse osmosis report and look at the diagram, you see we added a line showing that we're going to take a little permeate out and send it off to the UF system. And in this particular case, it averages out long-term to be 0.03 cubic meters an hour. It's sort of an average flow going back to the UF. So not much of an impact on the RO system, but much cleaner water to use for your UF cleanings.
Garth, do you mind taking a look at the mixed bed report?
Sure. We'll go take a look at the mixed bed. Okay.
All right.
So
go ahead.
Okay, the mixed bed report shows that we should get a runtime on the order of 39 hours. And if we look down into the middle of the report, we have potential runtime. It looks like the cation bed, part of the mixed bed, could run for 600 hours. Nice long runtime, but we're only getting 39 hours out of the mixed bed, the anion component of the mixed bed.
Do you think we could take a lock at the RO effluent just to see if CO2 might be a driving factor of that low run length on the anion resin? And if so, maybe we could do something, maybe just show one of the methods for mitigating CO2 out of the RO, either with a degas or by another means.
Okay. So here we look at the summary report out of the RO, and we can see that the CO2 is estimated to be about 8 ppm. The TDS, everything else, is 1.3, so the load on the anion resin is almost entirely coming off of CO2. So to eliminate that CO2, one technique would be to put in a degasifier. So we want a degasifier between RO and the ion exchange mix bed, so we would go to the mix bed screen, go up to where it says add chemicals. Notice you have an RO here and the mix bed here, so you can make sure you found the right degasifying location. We can specify now, select degas. We're going to specify a concentration. We know the feed concentration is about 8 coming off the RO, so we'll get ourselves a good degasifier and put in maybe half as much, so we'll get down to maybe 4 ppm of CO2. Now we rerun the calculation, having gotten rid of a substantial amount of CO2, and we should see that we get a substantially longer run length before we have to do a regeneration.
All right. Garth, while you're on this report page, there are a couple of things that come to mind. I was thinking maybe you could just show at the top where that temperature box is in the drop-down of design, and just show, it might not be fully obvious, but once you've already run your design, you can go up and select the minimum design temperature and refresh your report, or even change to a specific temperature and refresh the report without having to go back and change all of the design conditions.
Correct. So if we wanted to see the impact of temperature on the system, instead of changing your feed water, you could come right here and say we're going to run at the minimum temperature and just click on refresh report. It will keep everything you already designed, just change the feed water temperature, and you can see the impact of a temperature change as it propagates through your system. So on our particular design, it didn't have much of an impact on the mix bed. But it makes it a very quick way to see what the temperature impact it would be.
And in terms of impact, it'll also show changes in pressure drop and things like that as well. So, and just before you jump off, or maybe if you want to show one more thing before we do this, but even folks that I work with on some frequency, whenever I've sent them some of my reports after running a projection, I've gotten feedback that the report I send is a little more detailed than the report they generate. And I just wondered if you want to show people how to get to the detailed report. We don't have to dive too heavily into it, but just to show that anyone can get to that and see all the information that's in there.
Okay. So we're in the process of loading the detailed report. And then you can come here and change the size, we'll make it page width. And this gives you a much more thorough look at the design. In a multi-tech design, the first page is actually a summary, so you can actually see the water flow rates coming down the system and what each of the waste streams would look like. And in this case, you can see there's a small amount of RO going back to the UF. And then there will be a page for each of the technologies. The top of it looks very similar to the standard report, but underneath it you will find details on more details on flow rate. For here we show the pumps that would be needed for the chemicals, hydraulics, electrical consumption, cost per day for pumps.
And it's worth mentioning that information links back to some default values in the program in terms of energy consumption and cost of energy and cost of chemicals that the users can change as well.
Correct.
So, Garth, something that came in while you're working through this is what the purpose of the stacked report function is. I don't know if that's something that's quick to show or straightforward enough.
Well, I'll explain it.
All right.
So if you had generated multiple cases within a specific project, if you remember, Wave stores everything in a database. You have a project, and your project has multiple cases. If you were to go up to the stack detailed report, you could, with essentially 1 or 2 mouse clicks, generate a detailed report for every case in your project file and import it or export it into one large PDF file, rather than go to a project or a specific case, run it, print out the report, go back, get the next case, run it, print the report. Here you could print all of them with one mouse click, essentially. Okay. So that's what the stacked reports do for you.
And Garth, can you show us how to run batch reports?
Sure. One of the features of any RO design is you often want to check how the RO performance changes with temperature and how the RO performance would change as the membranes age and the permeability of the membranes age. So we have for RO designs what we call the batch processing option. Given your minimum, maximum temperature and a number of intermediate points, Wave will create essentially a grid of temperature and flow factor. In this case, we have 3 temperatures and 3 flow factors, so that's 9 runs. If we accept it, you can choose what options you want to see in the report. We had no boron in the feed water, so let's get rid of the boron. And you get this little table of temperatures and flow factor that you would run. So if you clicked here and create case, it would take all of those and create 9 new cases for you and stick them into your project file. Or you could just calculate it. Right now it's running the first design and locking down what the mix bed will look like. And now it's going to run every one of those 9 cases sequentially. And you can see you have a handy little spreadsheet table that you can actually watch what's happening inside your design. So this is a way to relatively quickly map out the performance of your system without manually going back and changing lots of inputs. So we just ran 9 cases.
To this, but this is an RO feature, right? You wouldn't use this with ion exchange. This is a feature that you utilize with RO, correct?
That is correct. This only shows up if you have RO someplace in your system. But if we, look over, for example, here's the permeate TDS coming out of the RO system. So it was, 0.97 at the low temperatures and 5.9 at the higher temperatures. So for an RO system, you can see how its behavior changes with temperature, which obviously would then change what goes into the mix bed. And if you wanted to, you could select several cases and then look at them in more detail normally. But that takes more time than I want to use on this little demo.
All right.
Well, it's pretty typical to need to run a case with a fairly high flow factor to show initial performance and at the maximum operating temperature to be able to show the worst case salt passage, and also to run a case that's at the lowest operating temperature and worst case feed TDS, lowest temperature, low flow factor to show aged membranes and show the highest feed pressure required to the system. And then a number of reasons why you might want to run intermediate points like you've done here, Garth.
Yeah, correct. Right. So this gives you a nice simple way to sort of map out the expected behavior over years and seasons. Okay.
Garth, are we ready to move into our next example?
Yeah, I believe so.
All right. So as you're getting back to your home screen, something that came in from the Q&A is if you can just show, we don't need to change anything, but if you can just pop up the box that shows how to change those defaults for the energy consumption and cost. I think that's worthwhile while we're on a home screen. But I'll set up I'll kind of give some intro as you're getting this loaded. Garth and I had talked about doing a condensate polishing example just because it lets us, it's going to let us get into some of the extra features related to ion exchange. So But we did kind of agree, Garth, and this is a way to show one of the features that we might change the units to US this time. You did one in metric, and then maybe we'll bounce back and show how this process works. But Garth's changing everything to US, and we're going to keep, I prefer bed volumes an hour as opposed to GPM per cubic foot, so I don't know if you want to select that.
So, yeah, so you can be pure metric, pure US, or some hybrid thereof based on your personal preferences. Okay. So we're going to start with our condensate polisher. And it's going to be 16,000 GPM. Now, we had the question about how to check the costs and things. So up at user settings, there's an operating cost button, and you can specify the cost of water and the cost of electricity. And if you go over to, well, actually, those are the same screen. And if you go over to here, you have, for example, the current price that's going to be used for the chemicals in your system. So if you think hydrochloric acid is much cheaper or much more expensive than the price we loaded several years ago, you could update the price, and that would be used for your specific project. If you update a price here and then click on this button down here, that would make the price change the default for any new project.
All right. Thanks, Garth. I think that's good.
Okay. So we started our condensate polishing, so let's go to the feed water screen for our condensate.
Okay, so Garth's going to put in some trace constituents as our feed water, but I just want to supplement here to say that a lot of times when I do condensate polishing designs, I will get from an OEM or an end user a pH value, and they'll mention that the pH is attributed to ammonia. And one of the features in Wave is that you can actually enter a pH. And so Garth's going to enter a pH. Garth, do we want to start with maybe 9.5 here? Garth can enter a pH and add ammonia, click the add ammonia button, and it will actually give an estimate of the ammonia concentration. Total ammonia and ammonium presented here as ammonium. Is that right, Garth?
As ammonium.
Okay. But that's a feature I use all the time, and you could do it vice versa. If you had an ammonia concentration, you could put that in and click the adjust pH button. And one question that came in, Garth, from the audience was about two things while we're on this page. One was when you were on the feed screen last time was about the pH and the accuracy out to that second decimal point, and there being a big difference between 10.7 versus 10.74. And in general, the decimals on this screen, can you just comment on what Wave takes with it?
Sure. We'll take a Wave is actually going to use the current water chemistry, and then as it goes through the process, as you start taking ions in and out with the different processes, your charge will become unbalanced. Wave uses the charge imbalance to determine what the pH needs to be to add hydrogen or hydroxide, and also affects equilibrium like the CO2 bicarbonate CO3 equilibria. So because of that, we're keeping lots of significant figures behind the scenes and everything. So the pH in this case is 9.50. It's actually 9.50000. But that's used so we can do a good job with pH swings later in the design.
I'd say that's good. The other thing is, if you want to pop, just while we're on this page, the condensate polishing additional parameters button, just to show, we're talking ammonia here on the main screen, but there is a whole additional set of factors where you can include some of the common organic amines. And then also you could add something like crud. And maybe for this design, Garth, maybe we could just add, 20 ppb or 15 ppb. Let's go 20 ppb of crud. But just a note here is if you do enter the organic amines, they will come back to the main screen as equivalents of ammonia.
Correct. Okay, so by the way, this is ammonia as ammonia. This is over here is ammonia as ammonium. That's the difference for the slight difference in weight.
Okay.
Okay, so we'll save that. And now I believe we can go on and design our condensate polisher. So we have a very high flow rate, so we're going to need to have much more than one train. So we'll put on 7 trains online and 1 in standby. Then one of the things we're going to do here makes use of a feature of Wave. We could design a standard mix bed, but for this example, we're going to design a system that has a cation pre-bed, which will be co-current regeneration, and then we'll have our primary mix bed, which will have externally regenerated.
Garth, is there a material difference whether you selected internal versus external here for generation?
Yes, there is a material difference, and as I go through the rest of the inputs, I'll actually show where that comes in. Okay. We just specified that we were going to have a cation pre-bed followed by a mix bed. So when you just make that decision, you get this special option here where you can do the cation solely based on time. In this case, let's say we want to go for a 7-day run length. And then we have the specific velocity for the mix bed, and these tend to run pretty high. So we'll run about 100 BVs an hour for our initial mix bed.
And this is a nice specific feature to condensate polishing that you can split these length of operating cycle and specific velocity for the 2 components here. But this is also just a nice general feature that you can specify specific or spatial velocity as you're doing new designs or time. So thanks, Garth.
Yep. Okay, the vessel has already been specified. We now have to choose our resins. For this particular example, we're going to choose HPR 1600H. That's the high capacity gel in the pre-bed to take up all that ammonia. And then for the working mix bed, or the condensate polishing mix bed, we're going to take the HPR 650H form and click here because I want the hydroxide form anion resins, and we'll take HPR 550OH. As we come down the regeneration conditions, we'll select sulfuric acid for the acid and caustic for the anion resin. Click more, you can see some screens. Here are all your regeneration conditions. We'll accept the defaults. We had the question a couple of minutes ago about what happens with external regeneration. You get this little tab here. You can specify the diameter of the backwash tower and the regeneration vessel that will be used for the anion and cation resins, and that allows you to decouple the diameter for the regeneration from the diameter of the service vessel. So if you need a certain linear velocity to get a good backwash, you can set the tower, and then you'll use more or less water than you would if you did it inside a normal service vessel. So it allows you more degrees of freedom to specify the system, and that will affect water consumption numbers.
Thanks, Garth.
So we'll take the defaults for everything else, and we'll generate our report.
And I think just 2 things, it'd be nice to look at the different throughputs as we go through here. And then for the mix bed, just show that was designed based on the spatial or specific velocity that we put in.
Yes. So the system, the shortest thing in the system will have a run length that you can see here is 168 hours. If we scroll down, we see that the potential run length for the HPR 1600 pre-bed is in fact 168 hours like we asked for. The mix bed, the first thing to break through looks like it's going to be the anion resin at about 600 hours. So we get a nice long run length off the anion resin. But we designed this bed based on specific velocity And you can see here that we targeted 100, and we got essentially 100 BVs an hour for the mixed bed. So we actually were able to specify the cation pre-bed on time and the mixed bed on SV.
So Garth, I think one more thing that would be good to show here is so we just did our new design. Can we go now and evaluate this design in, say, a condenser leak scenario?
Sure, Matt. So one of the tricks in Wave is we'll go back to our home screen, and having run a design, and you see we have here this final parameters screen, which appears after you've run a design, is if we click on Evaluate Existing Plant, you have the option here to make a copy of your existing design. So what we have just done is made an exact copy of that system. So that now, instead of a new design where if you make changes, you could change the resulting geometry and vessel size and resin volumes, we've now made a copy of it, and all of that information is locked down. So now you can make changes in your feed conditions and see how it reflect the performance of your existing system. Okay. So, Matt?
All right. So in this case, do you want to just add maybe a small seawater condenser leak? And this is not too uncommon that we might have a scenario where we've done a design and then we'll have the request to evaluate some different conditions than the base case design.
Sure. Okay, so we'll do a couple of things here. First, many people don't know you can actually change the name of a stream. So if you click here, you get a little pop-up, and I can call this the condensate. Now I'm going to add a stream. So stream 2, and we'll go into our water library and grab out the standard reference seawater.
And you could do this on any design, right, Garth? You could add a stream if you had two different source waters and you were changing the blend of them or something along those lines. Correct.
You can any design you can blend a number of streams together. This one we just we're going to use two streams. So stream 1 is your condensate. Stream 2 is your seawater. Now you specify how much of each you have. We're going to say we have a pretty small leak, which turns out to be only about 0.005 of the.
That's fair.
And then we'll come up here and we'll put in 99.995. Condenser leaks are pretty small, so they get rounded off, but it will, in fact, use the digits you can't see to do that. And then you end up with this other button called the blended composite. And so you can see that we have the same amount of ammonia we had before. You can see we're starting to bring in more sodium and chloride from your seawater, plus traces of everything else. So you can just look at your feed, your contaminant, seawater in this case, and your composite. And at this point, the only thing you have to do is hit Summary Report, and it will rerun the design using the water. So before we had 168, before we had the first thing need to get regenerated, now it's 93 hours. If we scroll down, we see that the cation went from 168 to 123, so we got some reduction in operating time for the cation pre-bed, but we had a large reduction in the anion performance of the mixed bed. Before it was 600 hours. Now the anion component of the mixed bed is only going to last for about 92 hours. So, but it gives you an idea of how the condenser leak would change the run lengths, and if you go back to the feed water screen and put in a larger or smaller leak, you could see how the run times would manipulate.
All right.
So
I'm going to let you and Kevin move it back to maybe some RO stuff. If one thing you want to do in the midst of that might be to change your units again to show how that works, but I think it'd be a good time to move into another example.
Okay. One last thing I was going to show is anytime you have a blended water, you will add a page to the end of the detailed report specifying each of your feed waters and what the blend is. So you can verify that we had a trace amount of, in this case, 0.8 GPM of seawater mixing in with our 16,000 GPM of condensate.
Okay.
And you can actually see how it calculated the blend. So sure. So I think that finishes this one. So
before you close this down,
sure.
There's a question about if you need to collaborate with colleagues, customers, how can you share the file in its native format?
Okay. There are two parts to that. First, you would go to File, and you would save the project with a name. And after you save it, you can then export it. So we'll just save this one as the default example. And that might take a little while as it moves everything from the into the final database. Project was saved, and then you hit Export Project, and you put it wherever you want to put it. And we'll stick it on my desktop. And it will have saved the file in this, what we call a DWPX format, and you can then share that with anybody. Okay?
Thanks, Bart. There's another question about RO systems and balancing flux. So could you generate a seawater RO case, and we'll look at how we can balance flux between stages and within a pressure vessel?
Okay. So we will close out the existing project. I'm going to go back to my defaults are metric. So with a new design, it went back to everything to metric. And I will do our seawater RO. So we will bring in our RO icon. Make it a little larger than the small plant. We'll go to feed water, and we're going to load in a standard seawater. And now we'll go over to the RO inputs.
And here, can you prepare an internally staged design? So within a pressure vessel, it's usually common to use the same element in all positions. But what happens is along the pressure vessel, the osmotic pressure is increasing. There's a pressure drop due to flow in the feed and brine channels. So there's less feed pressure available in the tail elements and a higher osmotic pressure. So they end up being a lot less productive than the lead elements. And one way to balance out productivity within the pressure vessel is to use a combination of different elements in different positions. So could you give an example of that?
Sure, Kevin. So while we were talking, I was setting up most of the rest of the design. So we'll go over here to where you specify an element. And one of your options is what we call the internally staged design. Brings up this other little pop-up. In principle, you could specify a different element for every position in the vessel. In this case, we're going to use the XHR 440i, and then it automatically fills to the right. And we'll take 3 elements of the XHR, and then we're going to put in some of the XLE on the back end. So we now have an internally staged design with 2 different elements with different rejections and permeabilities. And you could, as I said, you could have up to, 1 per every element if you wanted to go to 7. Let's see, we need to specify the elements for the second pass. which was this one. And now we want to make sure that we get the correct fluxes for each pass, especially in a seawater design. So seawater design is not going to run at 75. Let's put in 45% for the flux. And over here, we'll put 90 for the second one. And we know that the concentrate coming off of the second pass is actually much cleaner than seawater. So we're going to recycle all of the pass 2 concentrate back to pass 1's feed. So you can see that we have to recycle. And we now have everything we need to run the design, and we can run it. Okay. So a couple things. For example, in the stage level, it tells us we had an internally staged design. No warnings. That's always good. And at the element level table, you can see where it'll actually give you the different element names, so you can recall how you actually split it up. Now we got to the second pass stage report.
Okay. Hold on here for a sec. This was a question about balancing hydraulically, and we can see here on pass 2, looking at the average permeate flux, that there's about a 50% difference between the stage 1 and stage 2 fluxes. So can you show us how we might balance that? The goal of any good design would be to balance the flux as much as possible between elements in different positions.
Okay, Kevin. So there are 2 ways we could balance the fluxes. The first one is we could apply some back pressure on the first stage, which effectively raises the pressure going to the feed of the second stage. And as we rerun it, okay, and we could recheck, and now I have them balanced to about a fraction of a percent. So that's one way of doing it. The alternative way of doing it was, instead of applying a back pressure, one could apply a boost pressure. So put a little boost pump between the 2 stages, essentially accomplishing the same objective of getting a little more pressure into the second stage. You can see that essentially we got the exact same flux distribution, whether using a back pressure or a boost pump. There is energy differences between the 2 options because of the pressure that the main feed pump for the pass sees. In this particular example, if you were to go into the detailed reports and look at it, you save about 18% energy on the second pass by putting in an extra pump.
Thanks, Garth. There's one other possibility for balancing flux between stages that also came up in a question, and that is about a hybrid design. If you can flip back over to the reverse osmosis panel, and so we can quickly show how you might do a hybrid design. We don't actually have to run it here, but the idea is that you'd use a lower energy, higher flow type element in a later stage to draw more flow through to the later stages. So in stage 2, it would just be a matter of selecting the drop down and selecting a lower energy element to make a hybrid design in this case. Okay. And can we go back to the report and take a look at the RO chemical adjustment?
Sure. Yep. Okay, so we go back to the report.
So here we're going to go down and take a look at sparingly soluble salts. This is a seawater case for seawater and high salinity brackish waters with TDS more than 10,000 ppm. in the concentrate. We look at the Stiffen-Davis stability index, which is used to express the potential for calcium carbonate scaling. So we can see here that Stiff-Davis stability index is slightly positive, and ideally we want this value to be slightly negative in the RO first pass concentrate. So can you show us how we might do some chemical addition to bring that in line?
Okay. So Kevin, what you do is you go back to your reverse osmosis screen, make sure you're in pass 1, and you can then add chemicals in front of pass 1. And here we're going to use this first button to reduce the pH. We're going to use hydrochloric acid, and you can either specify a target pH or you could specify a target S&DI. So we'll target -1, and we want to make sure that we have the correct default recovery for the design, and that should give us a negative Stiffen-Davis index for the concentrate. So we hit OK and run. And then go all the way down to the bottom. You can see that our target Stiffen-Davis, I asked for -1, I got -1.01, and we do in fact have a negative Stiffen-Davis index in the concentrate to minimize chance of scaling.
Thanks, Garth.
Okay. So Garth, thank you so much. And for everyone on the line, we really appreciate you being here. We appreciate all the questions that are coming in. We're going to move into try and do some more focused Q&A here. And Garth, if you want to keep sharing your screen for just a couple minutes, a few questions came in about can the program show neutralization requirements in ion exchange? We don't need to go deep, but maybe just if you can show where that would be. Another question was, I'm just going to throw a couple at you while you're getting there, is if feed streams other than water can be evaluated in WAVE, something like, what about 8% sulfuric acid?
Okay, and okay, just noting the request. So a couple things. We go back to the feed water screen. We can go up to a concentration it's aqueous-based streams for sure. We can't handle non-aqueous streams. We can handle solutions with a TDS over 100,000 milligrams per liter. So we can start handling, semi-concentrated salt solutions. We can't take it all the way up to where you would precipitate, but for example, someone wanted a very concentrated sulfuric acid. Let me clear what's in the feed water stream. So if you click up here where it says this, there's 0. So I just cleared out the stream. If I wanted to say I had 100,000 sulfuric acid.
If I can just jump in and mention to the audience, if you can use this time while we're doing Q&A to download your certificate and things like that, once we finish up at the end, the console will close and that information or those tools will no longer be available. But we're still going to be here, so for a little bit longer.
Okay, so in this particular case, you can type in 10,000 milligrams per liter of sulfuric acid, and it predicts a pH of 0.87. Obviously, if you put in too much acid, we're going to have trouble at high concentration acids of getting, a reasonable pH. But I can get up to 10,000 without a problem. 100,000 is beyond the limits of the program. The other question had to do with how I could get a neutral. So let's throw out the RO, and we'll just put in a demineralizer. And this is not going to run because I don't have reasonable waters.
That's fine. I think if
we're just going to show where it would, how you would do it. We'll just take the first thing everywhere. Yeah, I'm going to regenerate sulfuric acid stream with sulfuric acid. Anyways, on the bottom here are several options of what you can do. So this one here, if you ask for a neutral waste effluent, it will run the design as specified, look to see if your waste stream is acidic or basic, lock down one of the doses, and then adjust the other dose up and down until it can find a final pH of right around 7. So that's how you would do a neutral waste effluent.
And someone, while you're on a screen like this, someone asked about when you added the degasifier, can you specify where that goes if you wanted it somewhere else? Can you specify where that goes in a system? And then a general question came in around if the Ligasep degasifier is going to be available in Wave.
Okay, so to specify a degasifier, we'll go back to our vessel and regeneration system. So inside the ion exchange icon, I can put a degasifier. Once I turn it on, you get a choice of after a weak acid, or after all the cations, before any anion, or after the weak base. So here you can specify the current location. If you use the Add Chemical button at the top, it would go between your previous icon and the current icon. So I could either, so depending on your design, you've got, multiple places where I could put a degas station. Okay. At the moment, we do not have the Ligasep in here yet. That's on the product plan to be added at some later point to put in the new Ligasep technology that
membrane degasifier.
The membrane degasifier that DuPont will be selling.
Okay. All right, thanks. Kevin, do you have a couple more? There's more that I could keep going with, but I want to give you a chance.
Yeah, there's a couple good ones here. Garth, is it possible to use old ROSA designs in Wave?
Excellent question. The answer is yes, you can import ROSA files. If you were to go to File, Import Project, down here in the corner you have the default is the DuPont project, the DWPX file, but you can also import a ROSA file. So if I happen to have any ROSA file sitting on my computer, if I had clicked on this, it would now, I could start browsing around to a ROSA file and it would import it. We cannot import the ion exchange files from CADEX or IXCalc, but we can import the ROSA files.
That's a great feature.
Yep.
Can you adjust RO permeate pH, Garth?
Can I?
Basically, there's a question coming in. Can you post adjust the pH of RO permeate?
You can adjust the pH coming off the end of the system, which is we have this little adjust final pH button, and essentially what you would do is turn it on, you want to do it, and say, if I need to add an acid, it will be that. If I need to add an alkali, it will be that. You target a pH, 6.5 or 7.5, and then when you ran the design, you would take your final permeate off whatever was your last technology in your stream, and then add acid or caustic as necessary to reach a pH of, in this case, 7.5. So At the moment, we do not adjust pH between technologies.
Okay. And Garth, I think...
Correction. If you have multiple icons, you can actually change do a pH adjust before the next one. So if I had the RO mixed bed, for example, and yeah, it's not gonna, I got to put something in the water.
Okay. So Garth, we're going to pause for a second. I just want to say thank you to everyone for being on the line. We're going to keep hanging out for a little bit. There's still a lot of questions coming in, but as folks start to drop off at the top of the hour, I just want to encourage you to join next week on Wednesday, May 6th. Laura is going to be doing an interview with a New York Times bestselling author, Seth Siegel, regarding his book, Troubled Water, What's Wrong with What We Drink. And there's going to be some a large number of free copies of autographed books available. I am excited to join. I think it's going to be a great session. I really enjoyed the last Blue Talk, and I'm excited for that one, the one coming up next week as well. So, but for everyone that's still on the line, we're going to keep going for a few minutes. There's still a good bit of questions coming in. Kevin, do you want Garth to keep doing the screen share? Do you want to switch back to video?
Yeah, Garth, are you able to open up the first multi-stage example?
The first multi-stage. Okay.
Do you have that archive?
What, that I showed today, or the one that comes with the program?
No, the one that you, similar to what you showed today.
Okay, the webinar example.
I think that would be useful to address some of the questions that have come in for RO, for ion exchange.
Okay. So here's our previous design. Okay.
Awesome. So one of the questions for RO is if there's provision for RO permeate pH correction.
Right. Okay. So the one I had sort of got a little wrong is if you have between icons, you can actually go, I forgot, you go up here. Obviously, you can do your degasifier here, but you could also do a pH addition or subtraction. So if I wanted to acidify my RO, I could add a little, hydrochloric acid and specify a pH of 6.5. If the pH is coming off the RO is above 6.5, I'll bring it down to 6.5. If it's already below 6.5, obviously adding acid's not going to help. But you could, in fact, if you wanted to specify caustic to 6.5, and then no matter what the pH is, you would bring it to 6.5 going into your mix bed. So you could use this sort of trick between icons. And then there was on the home screen, there was the adjust final pH, which is essentially the same technique for your final water at the end of the train.
Thanks, Garth.
Okay. Any other questions?
Are there some questions about antiscalant? If they can add antiscalant?
Okay. We'll go back to the RO screen. We'll go look at the add chemical for RO. And this one shows that you have, in addition to the usual pH down, degas, pH up, you can add an antiscalant here. You could add a dechlorinator, the sodium bisulfite. And what you can do is, we're not going to, WAVE does not try to calculate the correct dose of antiscalant for you. However, if you have entered any anti-scalant into Wave, you could select it at the drop-down box and then pick the dose you want, and then Wave would do the necessary arithmetic, saying this is the volume of water, this is the desired concentration of anti-scalant, and at the end of the detailed report, it would say you were using up 10 kilos a day of anti-scalant, and based on the price you gave it, it would tell you how much you were spending on anti-scalant. So this would then show up in our detailed report.
Garth, I think let's move back to the live video. I think we can. You good with that, Kevin?
Yeah, I got 2 more questions here that could make use of the screen share before we do that.
Okay, all right, go for it. If you want to go to the home screen, then Garth, someone asked about mixed bed polishers, just general. If you can just re-show that icon, that was one that came up.
What about the mixed bed polisher?
Just to show that someone asked about, can you just do a standard mixed bed polisher? If you can just, you don't have to get into the module, but just hover over the icon to show which one that would be.
Okay, if you want a polisher, it's this IXMB. If you wanted to do a working mixed bed under this IX demineralization icon, you could create a mixed bed in here too. So you could have a working mixed bed if you were to bring this in, and the IXMB as your polishing mixed bed. So you could, in fact, design a system with 2 mixed beds in series, a working mixed bed and a polishing mixed bed. And that would just require dragging this in like that. And then I would go RO, working mixed bed, polishing mixed bed.
Garth, one of the questions on the UF model is whether it can predict the TMP profile between cleanings and after cleanings based on feed water quality.
Okay. Okay, the program's now in the middle of trying to, there it is, add my IXD. Okay, so TMP profile. We'll go back to our ultrafiltration screen. Yes, that one extra icon slowed it down. Come on.
Garth, and I think after this one, we'll shift back to wrap things up, just to say goodbye to everyone.
Sure.
And Kevin,
we've essentially hung up my wave.
Did you ask about the let's drop the screen share. Did you ask about CCRO, Kevin, and its inclusion into the program?
No, there's a couple questions there. I think one was a follow-up on importing ROSA cases, whether ROSA cases involving CCRO could be imported. And there's a couple questions as to if CCRO is going to be included in WAVE.
Okay, so we are in the process of integrating the Desalotech CCRO technology into WAVE. It will actually be a new icon, and that's in progress. The importation of ROSA CCRO designs currently is not possible.
And then Garth, one question about the version. Some folks notice that you have a version that they don't necessarily have. Do you have any comment on that, and when the version you have would be available, or if it's already available?
Okay, so I'm running version 1.76. We're just finishing the testing of it, and the expectation is that we will be releasing it publicly very soon. Just fixing the last couple of bugs in it. So within the next couple of weeks, we should have 176 out. And some of the changes are that you might notice I had bromide and phosphate in my version of the code. And then there's some bug fixes and some things to improve speed and lots of other things.
All right. Well, Kevin, do you have any final questions before we wrap up?
So,
yeah, there's one more that I'll address quickly. It's about the difference between trains and skids in the UF model. So trains is any group of modules that shares a common valve stack, shares common instruments, and a train might be made up of multiple skids. We use this terminology to distinguish between the two when you're using like a pre-engineered option like IntegraPack, for example, where you can get pre-engineered skids with between 6 and 22 modules on a rack, on a skid. And you could combine several of those to make a much larger train as part of your plant.
All right. So just want to say thank you to everyone. Garth, great job today. We appreciate you taking the program live and showing everyone some of the features. I don't know, do you have any final comments? Just want to say thank you, everyone. Goodbye. And we really appreciate your engagement with all the questions and joining us. So Kevin, if you want to say bye, and then Garth, any final words?
Hey, thanks, everyone.
okay, and thank you everyone for listening in. And if you have any questions, please pass them on to our functional mailbox, which is ffewave@DuPont. And we'll be glad to answer them. Okay, goodbye everybody. Have a good day. Stay safe.
Bye, thanks.